Welcome. It's been 2 years, a little under 2 years since we released MacFUSE at Macworld 2007, and a little over 2 years since I first thought of doing this. And it's come a long way since then. A lot of products and projects are built using this. Big products like VMware and Parallels, they use it to implement some of their features. There are other products like Missing Sync and Stuffit that use it for implementing their features. There are products that are entirely based on this. Expand Drive is one example. There are research projects. There's toy projects. There's like not-so-toy projects. People just trying out, different ideas that they couldn't before on macOS 10. So it's very heartening to see people put this to the uses that we thought they would, and in many cases to uses that we didn't even think they would. So that's been great. Now, of course, if you look back and you're strategizing, what else you should do to make this more successful, make this more useful. So one question I ask myself is, why this has been successful, or why people like it, those who like it. So I look upon MacFUSE, at least now, I look at it as a battle against complexity. Complexity in operating systems. Now, this is nothing new. Complexity in operating systems, it's plagued technology forever. Ever since the advent of Unix and the popularity of Unix. People have been fighting against complexity. People have been complaining against it. And then, things go back to where they were. Because all solutions to whatever complexity people are fighting against, they end up being more complex than they were to begin with. Now, so let me give you, I want to quantify this. Or I want to give you an example where you can actually look at some numbers to visualize the kind of complexity I'm talking about. So look at this number. It's a small number in today's times, 24,696. Now, this is the size of a 5th edition Unix kernel from, over 30 years ago. Now, in comparison, this is the size of the macOS 10 kernel. And the bar is, it's not a progress bar, it's the relative sizes. The red one being ancient Unix and the blue one being macOS 10. So quite a difference, huh? We could look at some other things. Number of system calls. Or how many file systems, this thing supports. And macOS 10 does not even support, so here I'm counting the ones that come with macOS 10. I'm not counting, the hundreds you can have at MacFUSE. Or how long a file name can be. Or how big the source code for the Unix shell is. I mean, look at that. What are we doing in the shell anyway? And number of possible files in a volume. I do not have the pixel resolution to demonstrate this. So yes, very complex. And it's not just complex, it's also ironic. So if you look at the, I can put the philosophical history of operating systems on one page. So if you start at Multics, let's say, and many good things in Multics survived in Unix, and what have we done since then? We have done this. Nothing else. Every system ends up eventually being a reimplementation of Unix. Because it has to be compatible, open, close, read, write, work well. Even Windows, for that matter. They're very different in their UI. They're very different in, how they implement some of the things. But at the end of the day, now, you could counter-argue that, so how else are you going to do it? Well, I don't know. But we could research that, and the research shows that this is the way to do it. So this poses a problem, though. So yes, I mean, things are very complex and everything, and this is where MacFUSE comes in. So complexity is okay. You know, we have simplified some things. We have much better programming tools. We have much better debuggers. We have much better tracing technologies and everything. Now, files and directories or files and folders, and just the basic concept of a namespace and basic concept of storage that lives somewhere. You know, that's a very powerful, old, and simple concept. And it's a concept that everybody, like users, are very familiar with. Like, who doesn't know how to work with files? Like, everybody knows how to save files and create files and whatnot. And in the almost 40-year life of Unix, people have written, you know, lots and lots of tools that work with files. So it's a very compelling interface. And, you know, back in the days, like with Plan 9, with microkernels, of course, people realize this, the developers and the researchers, they realize this, that, you know, files are very powerful. Why don't we make writing file system easier so that developers and users can have more things at their fingertips when it comes to file systems and what you can see in your file system namespace. And, you know, unfortunately, we're not using Plan 9 today, but, you know, this has kind of been the holy grail. You know, people try to do it again and again. You know, user space file systems are not new. They've been tried many times. Even before MacFUSE was there in OS 10, you know, Apple used like the FTP file system and the WebDev file system. So they are done. They're implemented using, you know, similar concepts. The FTP file system uses a user space NFS server, and the WebDev file system, which you use for iDisk, it uses a user space component that actually does the network communication. But still, writing file systems is extremely hard. And even if you know how to write one, or even if you figure out how to write one, maintaining it. So it's very difficult to write because, you know, there's so many interfaces involved. You have to work with virtual memory. You have to work with the system calls. You have to deal with so many nuances and caveats. And then you have to program in the kernel, and then you have to debug in the kernel. And kernel code is not just difficult to write. It's very difficult to ship and maintain, especially on Mac OS 10, where there's not a precedent. Like, not a lot of people write kernel code in Mac OS 10. So shipping it, updating it, managing it is extremely difficult, and I know it from experience. Think of like an empty file system, you know, that just satisfies all the interfaces. It does nothing. It just mounts and doesn't have any content. So just a proof of concept that you know how to write a file system. So if you did this on Mac OS 10, my estimate is that you would need at least 1,000 lines of code to do this, just to satisfy everything. If you did it right, like if you put everything in place, just empty stubs and whatever. In contrast, the entire Unix file system, the actual on-disk file system code base for 5th edition Unix, since I talked about that, is about 700-800 lines of C. Now, even with all the evolution and whatever, that's a hell of a difference. Also, you know, if Mac OS 10 is Xcode and interface builder and the template stuff, it's supposed to make things really easy for you. If you're not doing anything, you shouldn't have to write any code. If you're doing something very simple and small, then you should have to write some simple and small code. Now, it's not like that with file systems, and that's where MacFUSE came in. What it did was it gave you interfaces that if you want to do something very simple, let's say you want to work on a backup utility and you don't know how it will deal with a file that's 2 terabytes in size, 16 terabytes in size. You may not have 16 terabytes of disk space. So you could write 50 lines of code, maybe less, and create a file system that has a 50 terabyte file. And it's a real file as far as this utility is concerned. So you couldn't do this before. You could do this now. And then things like cloud computing. Everybody wants to do cloud computing today. Everybody wants to take resources that are elsewhere. across the network, fictitious just in memory, and they want to put them on your desktop. They want to integrate, make everything seamless. And how do you do that? There have been some idiomatic solutions in the past. Everybody would just use like an NFS server or a WebDev server or a Samba server. And those things have drawbacks, and they're quite complicated too. Writing a user space NFS daemon is not as simple as it should be. So we've been very happy with how things have been. You want to write a simple file system, it's extremely simple to do that. And it's simpler now and more powerful now, today, with MacFUSE 2.0, which is available actually as of this moment, or an hour ago, I think. So what is new? So I want to talk briefly about what is new in MacFUSE 2.0. So step one, the biggest thing that our users wanted was not more functionality or interfaces or APIs, they just wanted to know how to install it, or how to uninstall it, or how to keep it up to date. Mac OS X users are special. They can be very demanding. So we have a preference pane. It lives in your system preferences, and it'll tell you when there's a version. It will not do anything automatically. It will do what you tell it to do. So we hope that this will make a lot of our end users' lives easier. We're quite happy about that. The other thing is that you're used to the templates that you can have in Xcode. You want to work on a QuickTime project. You want to work on a Cocoa application. You go to Xcode, you choose a template, and you have a lot of boilerplate code that you can just add to. So beginning with MacFUSE 2.0, you have a bunch of templates that you can see in Xcode. And then you can use it to write both C and Objective-C based file systems. It should make your lives a lot easier, because it is a big pain to actually set up the project. MacFUSE so far works on Tiger and Leopard, although I personally don't have much time or interest in maintaining it for Tiger, but it continues to work, so why not? Beginning with this release, it also works on an OS that shall remain unnamed, because I'm under NDA. But if you have it, it'll work. And there are a few other nice features. Let's talk of interfaces. So MacFUSE has a low-level interface. This is a superset of the Fuse interface from Linux. So if you want to write a file system that actually deals with, like you want, as a developer, you want to deal with files at the inode level, then you use the low-level interface. There's a high-level interface, again, a superset of the Linux Fuse interface. This deals with path names. So depending on your file system, how simple it is it disk-based or not, you may want to do this. For a lot of pseudo file systems that have content in memory, this is more suitable. And then we have a higher level interface, which is very much like NS File Manager. So if you're a Cocoa developer, if you've worked with NS File Manager before, you will be at home working with this. 64-bit or 64. So, this has been a very popular number with OS X in the last couple of years. MacFUSE 2.0 has 64-bit support throughout the stack. You have a 64-bit library. If for some reason you want to write a 64-bit file system, it also has a 64-bit kernel extension should you need one. It also supports 64-bit inode numbers, which is actually different from 64-bit support, but since I'm just talking about the number 64 here, I'm clubbing it together here. So you may not want 64-bit inode numbers. 64 bits are huge. At least in Leopard, though, if you use 64-bit inode numbers, you will also get a bigger stat structure. So, which means you will be able to fit more data. You will be able to return more attributes in a single call, as opposed to, say, you were not using this. So there's some documentation on this, and in most cases you would want to use this. There's a difference though. Instead of linking against the normal library, you will have to link against a different library. Again, this is in the documentation, but unless you have a good reason not to, please use this. A lot of our users have complained in the past that that when they're using a file system that's network-based, which means the content actually lives across on the server, they expect things to catch up faster, more often, better with the changed content if the content is actually changed on the server. So they actually want like a real network file system like NFS, or which actually has a server-side component. So here, let's say you're using SFTP file system. There is no server-side component that knows that it's a file system. So how do you know that something has changed? Well, you know if the user space daemon is diligent in keeping up to date with at least the modification times of the remote files. So you know that modern OSs have buffer caches and all, and they're greedy and they remember data and they don't want to forget it. So what needs to be done is that if a file has changed remotely, then what's in the buffer cache is not valid anymore. So the content needs to be refreshed as and when needed. So MacFUSE does a lot of it automatically for you now. So if you return the correct timestamps, then it will do the right things. So if the file size has changed, the contents has changed, it'll purge the buffer cache. It will even send out, file system notifications. Let's say the file got extended. So the effect will be that of as if a write happened or something like that. Some people have wanted to implement multiple file systems in a single process. So you just have one application, but let's say you want to implement 10 different file systems in it, all running in different threads, each one potentially running multiple threads. You can do that with MacFUSE 2.0 if you want to. I don't know why they implemented that, but if somebody wants to use it, sure, why not? So far, it was not possible to actually debug within the MacFUSE libraries at the source code level. So of course, MacFUSE is open source, but the official binaries do not ship with DSIM bundles. Now they do. So if you want to step into the libraries, you are not sure if it's your bug or ours, feel free to step into the libraries and debug at the source code level. DTrace is another thing that for the most part, you don't really need to do anything special to make use of DTrace. And that's true with MacFUSE as well. Most of the library functions have predictable signatures. So you can actually match on the function names and essentially get a really nice trace of what's going on, except that if you're using higher level interfaces like Objective-C, then if you want to actually introspect the NSString path names and such, then DTrace is not going to tell you because you don't know the internal structure of an NSString. So for that, the library now supports DTrace explicitly. So it has built-in probes, so you can, if you want to use DTrace, you can enable those probes and get really nice-looking stack traces with all the information you could possibly want. And again, you can do that at any interface, C or Objective-C. And we have much better documentation, or more documentation. So these are some of the developer features that we have. So to recap, 64-bit throughout, runs on 3 generations of macOS 10, really easy to manage, install, and uninstall, and new APIs, templates, and debugging aids. Now, when I mentioned that we have this bunch of APIs, low level, high level, and higher level, and I also said that so one of them is specific to macOS 10. The other 2 are supersets of the ones that are on Linux. So what do I mean by superset? So what I mean is macOS 10 has a lot more or different metadata. For example, it's got 5 timestamps that you can have. It's got different kinds of extended attributes. It's got custom file formats like webloops and whatnot. So the new API, so the additional part in the superset lets you do that. So for example, things like exchange data. You just want to swap the contents of the two files. It's a common pattern for saving files and whatnot. So exchange data is not there in Linux. But if you want to use exchange data in your application, you want to write a file system that supports that, you can. And I will ask Ted now to come and show you some things, and he will talk about a little more of this.
Hi, I'm Ted. I mainly work on the MacFUSE Objective-C framework as sort of a 20% project for me here at Google. And so I'm going to focus on that during my section. So my feeling is that, and I'm probably a little bit biased here, that the Objective-C API is probably the easiest and best way for seasoned Mac developers to start using MacFUSE. It definitely brings a few advantages. So basically, if you're writing file systems in Objective-C, you can take advantage of all the native Objective-C frameworks that are present on OS X, parsing XML, NSURL connection, all that sort of stuff. The Objective-C framework also adds some features to handle some sets of resource fork items and finder info for you, so that you can basically get custom icons showing on your files, and you can have weblooks and things like that. So it makes it very easy to do that sort of stuff as well. And I'll show you an example of that in a bit. So for MacFUSE 2.0, I've been actually fairly aggressive in changing the Objective-C API. Most of the changes are pretty minor, but I felt that they were necessary to have the API actually, work really well. So for those of you who are actually using the Objective-C API, don't really worry, because we're using Objective-C and there's some level of late binding there, the code actually will detect whether you're using the new methods or the deprecated methods. If you're not using the new methods, it'll call the deprecated methods and still do the right thing. But I do want to put out a little bit of a word of caution that at some point in a future MacFUSE release, I'll just get rid of the deprecated calls. And that's simply because there's a lot of overhead in maintaining that and testing that. And this is a part-time project for me. So in January of this year, I gave a talk at the local CocoaHeads chapter, which was recorded, where I talked a little bit more about the Objective-C library and I basically went through a tutorial. And during the talk, we wrote a simple file system called YTFS, or YouTube file system. I'm not going to make people go through that experience again, because it's kind of long. But I would like to at least show that so you get an idea of what can be done with the Objective-C library, if I can find it. Is it mirrored? So basically, this is showing how you can use the Objective-C library to make a Cocoa application file system, which that might seem strange to people who are really into file systems, having an application be a file system. But I actually think it works out pretty well on OS X. So basically, what I did is I had the Xcode project open, and I hit basically build and go, but it was already built, so it went. And what it does is, when the application did finish launching, or whichever the proper notification or method is, it basically goes out to YouTube and fetches an XML feed of the top 11 most highest rated videos. And then it throws them into a dictionary and then basically hands that off to the file system, which starts serving the data. And so you can see it mounted here where my cursor is. And this is actually showing an example of, as soon as they load, how to do thumbnails and weblooks and stuff like that. So I kind of think it's a neat example. So basically, when you mount the file system, it's getting the top videos. It's a real file system serving real data, and they are weblooks, so you can just double-click and watch your favorite videos. This guy's pretty neat. And because it's actually coming from a real file system, it's actually serving the web look and the custom icon from the resource fork. You can actually just drag the file out to your desktop, and it's just the standard Finder copying the data out, and it still works because it writes the resource fork exactly as it was coming served from your file system. And as I said, it's an application, so if you quit, it'll unmount the file system, or you can just unmount the file system and your application will receive a notification and then it can quit on its own. So that kind of gives a flavor of what can be done with the Objective-C library. So let me just take a quick run through the code so that you can see, essentially I don't expect you to be able to see from back there the actual lines of code, but I just want you to see the volume of code. Because if you remember, Amit was saying that he estimates it takes about 1,000 lines of code to create roughly an empty file system if it's a kernel level VFS. And here we have some classes that are serving YouTube FS. So these bottom two that I'm highlighting here is called NSImage plus icon data. It's a category. That's actually BSD license code. It's in the MacFUSE tree. And you can do with it whatever you want. But basically, it takes an NSImage and it returns the raw data for .icns. And so that's basically how I'm basically creating the icons that are being shown. So it's a little bit of helper code. And in this ytfs filesystem.m, this is the actual code that's serving the file system. So with the Objective-C framework, you basically create an object that implements some set of delegate methods which handle file system operations and serve the file system. And in a sense, actually, for a read-only file system, you can typically pick and choose which delegate methods you want to implement. You have to implement enough to get a real read-only file system, but I'll get to that in a bit. So if we just look at the volume of code here, I'll just highlight, this is the code that's serving the file system. And that's it. So that's about 50 lines of code to get something that's showing, web looks, and you can drag it out and double-click on it and stuff like that. I'm sort of cheating because there's a little bit of extra code here to access the XML and to parse it out, but that's like maybe another 40 lines of code or so. And then we have the controller class, which is what helps it make it into an application. And so this code basically handles mounting and unmounting and basically starting and launching it as an application. So that's like another 50 lines of fairly standard boilerplate code. It's code that I reuse for all my application file systems. And then we have another, I guess it's another 50 lines of code here to actually go to YouTube and fetch the feed, right? So you can see that basically you don't have to do a lot of work to get kind of a neat, at least in my opinion, a neat file system running. And again, it's a standard Cocoa app. And actually, for me, since I actually typically don't do Objective-C coding full time, actually wrestling with Xcode and Interface Builder and setting up the project and all that stuff is kind of a big pain point. So this is kind of why we went and did the templates. And so let me show you a quick example of that, because I can't go through a talk without actually writing a file system in front of people, because I guess that's what I like to do. So let me go to, so I'm going to a new project, and you can see our user templates are up here. I would have preferred maybe if they appeared at the bottom, but that's the way they appear. And so with the new templates, what you can do is you can quickly create, we have one for a C command line. So this is basically the standard extended Fuse API on OS 10. It sets up sort of a C command line program, which is, I guess, the way that a lot of the traditional Fuse file systems have been written. We have an Objective-C command line file system, which is similar, but it uses the Objective-C library. And I added some additional code in there so that it supports an icon when you mount it. It sticks it into the resource fork of the binary, so it reads it from there, actually. And then the one we're going to use right now is Objective-C file system read-only. So as I mentioned, when you're creating an Objective-C-based file system, you basically create an object and fill in a bunch of delegate methods. So the read-only version is, first of all, you tell it to mount read-only, and you only have to implement the read-only methods, like contents of directory at path and attributes of item at path, but you don't need to implement a write or rename or anything like that. So we'll start our file system. I guess it's going to go on the desktop. Okay, so there we have our template, and I hit build and go, and there it is. So there's our file system for today. I'm not going to write any more, but it really is a plain old empty file system ready for you to fill in whatever you want your file system to do. A very quick tour of this source code. If I start with the controller, you'll see it's pretty much the same code as the YouTube file system. So this is stuff that you don't have to rewrite over and over again. You just sort of insert a hook to initialize the file system as you want. Like instead of just plain old init, you can say init with videos, which is what the YouTube file system does. And it basically adds you some, this is the code that you need to fill in to actually serve your file system. And you can see that it's got the delegate methods there, and it's trying to do some sane sort of default things like contents of directory saying enoent, like does not exist. And you basically need to go in and fill whatever you think you want your file system to do. And there's something else I'd like to point out while we're here, which is documentation. So I added a link to the documentation in there, so you can click and see that we now have documentation on the Objective-C library. Let's see if this green button does it. Yeah. So this is basically header doc documentation. And you know, it'll probably evolve over time and get better, and that's something that people can hopefully submit tips and see what they want to have improved. But as an example, the file system operations is what your file system implements to serve the file system. And you can click here and you can see what all the operations are. So example, attributes of item at path, and you can see these are all the keys that you could return to describe what's going on with your file. The NS file creation date is actually something new that's supported now because the Objective-C framework is linking with FUSE INO64, which is something that Amit mentioned. So that gives us a bigger stat structure so we can support file creation date. Also, to be clear, the Objective-C framework is also 64-bit capable. So feel free to make your 64-bit file systems in user space. I just want to make sure I'm not missing anything here. Okay, so something else that comes up frequently in the MacFUSE mailing list is basically people trying to create writable file systems. And there's a very low barrier of entry to creating a read-only file system. But when you want to add write support, that's when you start running into trouble. And the reason is, I think, because they want to get something working too quickly. So what I said in my previous talk is that in order to implement write, you basically have to implement pretty much everything, or it's not going to work. You basically need to support makedir, armdir, rename, write, of course, and many operations. And another sort of related problem I see is that people create their file system and immediately start trying to test it in the Finder, which is a very bad thing to do. Because the Finder is doing a lot more operations than you think it is when it's doing something. So I recommend to people that they start off from the command line, testing individual operations one at a time. And you can do that for most operations just using standard commands available at the shell, like touch and chmod and chown and stuff like that. But let me give you an example of why I'm saying this, that you have to implement everything. And in order to do that, sure. Okay, so in order to do that, we're going to make use of the new DTrace support that's in the Objective-C framework, and something that I call a reference file system. And actually, let me discuss this for a couple of seconds. We have two sort of reference file systems for MacFUSE that are in the source tree. There's one under the file systems directory called loopback, and that's basically your C base reference file system. And there's one in the Objective-C directory, Filesystems-Objective-C, called loopback-fs, which uses capital letters. And that's the reference file system for Objective-C. So you should be looking, as a developer, you should be looking at both of these file systems for inspiration. But I think even more importantly, you should be using them to learn what the file system's doing. If you're having trouble and you're trying to use you're writing a file system and you're trying to immediately test with the Finder and things aren't working, one of the best things to do actually is to take advantage of DTrace and these reference file systems and see exactly what operations are going on to try and figure out what it is you need to implement and what you need to get right. So we're going to try and do that right now using something that seems trivial to many people, which is the save as operation in TextEdit, right? And we'll use DTrace to see sort of what goes on when you do a save as, because it's a little bit more tricky than you'd imagine. So I have loopback-fs running, and essentially it has one file called foo. And I should mention what loopback-fs does, and that's basically when you start it, you give it a directory, and it loops all operations back to the real file system in that directory. So you access it through /volume/loop, and whatever you're changing and reading is actually being changed and read from, say, /temp-t, which is what I'm using here. I'll fix this in a second. Okay, so I'm in the loopback-fs directory right now. And there's a file here called loop.d, which is a DTrace script. So before the presentation, I pre-canned a text edit that's open to a file that's on my loopback file system. So I'll start off running DTrace to grab a trace, and then I'll do a save as, and then we'll see what happens. So you can see that this DTrace script is actually pretty small, and all it's doing is saying, for all the DTrace logs that the Objective-C framework is dumping, just print them. And actually what it's doing is it's prepending a timestamp. So I'm just going to run the DTrace script using sudo, because you have to run as root. And I'm putting it into a file called /temp/d. And hopefully I know the password. Okay, so that's running. And then I'm going to get my text edit, and I'm going to add a 2.0 to MacFUSE and hit save. And then I killed my DTrace script. So what it does is it outputs one log line for every file system operation. And so here we see that we got 95 operations happening during our save as process. So this is a quick caveat. If you have a multi-core system, what DTrace does is it uses threads in the kernel. And so when it's logging stuff, you don't necessarily have the DTrace output come out in the order that things executed. So that's why the loop.d script is actually explicitly dumping the timestamp. So we can sort -n to see things in order, right? So again, I don't expect you to read this, but just I expect you to sort of get an idea of what's going on. And some of these actually might not be directly related to the save as, but you see at least 30 or 40 operations on a save as, but it's actually a lot. Oops. Hold on 1 second. Okay, so what I've done in this other temp, file and I put in temp is I basically have boiled the set of writable operations that occur when you do a save as, so that you can see I've essentially translated them into the sort of roughly the bash equivalent. And so you can see just in that simple file save as operation, you need to be able to support makedir. And in fact, it creates multiple levels of directories in order to create a temporary file for saving process. What I left out here is it actually will do a chown on this folders.501 to 501. That's your user. And then if you want to simulate creating a file and writing, you can just use echo some data to the file. after it writes the file, it'll set the U-times, so you can use touch to sort of set, at least test setting the U-times to the current time. It'll do a chmod, so you should do that as well. Yes? Oh, sorry. And then it'll do a rename operation, which you can simulate using move. And then I threw in a stat here just so you can see. I don't know if you can actually read the text, but all through this process, what I've left out is it's statting everything all along the way. And I believe I've seen Finder actually fail operations if you don't have the proper stat data. So I think maybe it checks its work, but I'm not sure. And then you need to have an armdir, right? So just in order to support save as in TextEdit, you need to implement a lot of writable operations, and you need to do that properly and return proper errors when you actually should be returning an error. So this is an example of why you need to do that, and also a quick example of actually using DTrace to see what your file system is doing. Okay. So that was TextEdit save as. I think what I've seen is that there's some typical save as patterns on OS X. But for example, if you want to support Word, Word can use exchange data. And so thankfully that's now supported in MacFUSE 2.0. And I think actually Word does have a fallback path. But there are some subtle differences. And so you actually need to figure out what you want to support and do some testing using one of the reference file systems and see exactly what it does. Word also will, at least what I observed is it'll open the file, write some data, close the file, stat the file, open the file, write some data, close the file, and repeat many times, and then it finally does an exchange data with the temporary file that it had created. If you looked carefully at the DTrace that I threw up when it flew by, you'll see that there's some calls, at least in the Objective-C library, to set attributes of item at path. And you may have noticed that it's actually setting multiple attributes at the same time. So those of you who are familiar with the C library, this might be kind of interesting, because with the C level library of Fuse, you would actually get separate calls, chmod, chown, U-times, one right after another. So what's happening here is that the Objective-C library is taking advantage of something new that's in MacFUSE 2.0, which is the setAttr_x call. And that actually is something. It's an extension to the Fuse API, an example of how on OS X we can better fit what's actually going on in the system. And what that call allows MacFUSE to do is to send up to your file system saying, I want you to set a bunch of different attributes, and it sends a bitmap of what attributes you should actually be setting. And this can actually be a pretty, I think, a decent performance win for file systems, especially file systems that have their data stored over the network and keep all the metadata synchronous. It's much better to be able to set all the operations at once than one after another. The previous incarnation of the Objective-C library would actually just call set attributes over and over again, one for each chown, chmod, etc. But now it's definitely much better. Yeah, okay. So that's basically pretty much everything I wanted to talk about. I just wanted to do one more plug for the reference file systems. If you feel like you found a bug in MacFUSE and you want to report a bug, it's very helpful for us if you go to the C loopback file system and try and recreate it there, and then sort of give us a reproducible case. If you can recreate a bug in the loopback file system, the reference file system, then yeah, it's probably a bug, and we can definitely fix it much more easily than if you just report something as a bug without giving us context. Amit?
Thanks a lot, Ted. Okay, demo time. So, you know, I thought a lot about this. Every time we do a talk, well, we don't have to, but we sort of want to come up with something that's cool, something that's interesting, something that shows off what you can do with this stuff, something that's not been done before. So when I'm in a bind like this, I often like, if you've read, you know, book of mine, or if you read some other writings I've done, you probably know that um, I like retrocomputing. I like going back to how things were because, things haven't changed a lot. And it's always good to remember what's new and what's not, and very little is new. So let's go back in time. And, since we're going back, why not just go back to the beginning of everything, and as far as operating systems are concerned. So I'll just like to take a couple of minutes and walk you through the thought process I went through when I was trying to select, okay, I want to write a file system, I just want something cool, so what should I choose? So I decided to look at ancient Unix. And ancient Unix had, and Unix today has, a lot of data containers. Data container being anything where you put your data. It could be a file system, it could be a tape, it could be a file system dump, lots of formats. So I'll give you like a crash history, rapid history of file containers or data containers in Unix. So this is almost 40 years ago. So, of course, the first Unix had a file system. This is the file system I alluded to, a few hundred lines of code. It had the concept of inodes and, block numbers and files and directories, and very much like what we have today, except very limited. 16-bit file sizes, 16-bit inode numbers, 8-character file names, so very limited. They also had a tape format, how you put data on tape. So they used to have these deck tapes, and the format on the tape was called tap. You will notice that because everything was very slow and limited, so everything was suppressed to fewer characters. So if you look at ancient code, you will see that the compiler itself supported keywords that are very small, like variable names and all. So commands are named in cryptic ways because of that. So then the library format, the R format, which many of us would know from like how we store static libraries, that was there in the first version of Unix. And the tap format actually, so at that time, they didn't know how they should store time. They didn't actually expect, they didn't know how long Unix is going to live. So they actually stored time in 60ths of a second, which is higher resolution, not full seconds. And it was 32-bit, but then it would run out in like 2 years. So they realized next year that, and I don't know if Ken Thompson is here. Well, he's not, so he can't correct me. So when they realized that, this is going to run out, and Unix has survived for so long, so then they decided that the epoch, well, why don't we just move it to 1971? And then why don't we just move it to 1972? So they kept moving the epoch, and eventually they decided, look, we should not store time in 60ths of a second. Let's just store it in full seconds so it can last for a long time until 2038. And let the epoch be 1970. So they had a newer format called NTAP. I don't know if it was officially a format, but this uses a 1970 epoch. And well, then the next generations of Unix, 4th edition, 5th edition, 6th edition, they had a newer file system, bigger file names, 14 characters, 24-bit file sizes, a few more things in there. The tape format was different. It was called TP instead of TAP, so even fewer characters, but it supported longer path names. And it had a few more things in the on-tape format. And then they realized they need still longer path names, so then they had 2 subsequent tape formats called ITP and DTP. And you can find ancient images, tape images, disk images in all these formats. 6th edition was kind of important in that it was the first version of Unix that was ported to anything other than a PDP. It was ported to the Interdata, and it also gave it also led to Xenix, and it led to something called PWB Unix, Programmer's Workbench, and this is where CPIO was born. And at that time, so tar and CPIO formats like these, they actually use ASCII headers today, which means that you store things in them like dates and modes and whatever. You actually sort of printf it into string and store the bytes because they're portable. There's no endian issues. But the first CPIO format was actually a binary. And then there was the 7th edition, even better file system, bigger file sizes. Blocks were 32-bit. There was also tar. Tar made its first appearance. And there was another version of R which was, more powerful, bigger, better things in there. And there was also a file system dump, which is essentially, you can think of it as serializing the file system. You have inodes and whatever on disk. So you just go through the file system and you dump the on-disk inode information and all the blocks following it, and you do that for the whole thing. So this was the only way you can, you could dump the file system, you could new FS, create a file system again, reformat it, and then dump it back. So this way you could grow the file system. So dump and restore were utilities used to do that. And 7th edition is really important. It can really be considered as the spiritual ancestor of a lot of things we have today, including in the file system realm. And then I ran out of space to show the lineage, and I wanted to keep it to one page. So, there was 32W, which was the 32-bit port of Unix to the VAX, and they used, the file system was also 32-bit, and they used a bigger block size too, or you could use a bigger block size as well. And, so the 6th edition also led to one BSD, the very first BSD ever created, and so all this while, BSD also was flourishing. They were doing bigger and better things with BSD. So there was a BSD file system at UCB. They used bigger block sizes, 1 kilobyte instead of 512. Then I call it BSD VN for variable name. So far, until this point, Unix file system was limited to 14 characters in length. And then this BSD VN I'm talking about, you could go up to 63 characters. This is the 2.11 BSD ported back to PDP-11, and it had symlinks. And there was a dump format for this too. If you dump in, the on-disk format is different. And then they had other versions of tar. They decided to standardize tar, so Unix standard tar, US tar as you call it. And again, there's a couple of generations of that. There's another generation of archive, more generations of CPIO, and the last version of Research Unix, which is V10, came out in '89. They actually used a 4 kilobyte block size, but this is a descendant of the 7th edition file system. And this is kind of where, if you arbitrary, actually not so arbitrary, I think it's a fair divide. So this is the ancient Unix history of file containers. And not everything is ancient, because things like tar, R, and CPIO, they actually continue till date in the same format. So the last versions I've listed here actually are the same as what we have today. So I looked at this, and I wanted to pick one thing and implement it, re-implement it for macOS 10, because obviously we haven't mounted an ancient Unix disk image as a real file system in macOS 10. So I decided to go with V6 file system. Again, it's kind of important historically, and it's also described in the famous Lyon's commentary in Unix. And even the design of the Unix operating system, Maurice Bach's book, that talks about essentially what is this file system. So it's beautiful. It's very classical. It's simple. It can be understood by one person in one sitting. And I wanted to keep things simple because I also wanted it to be an example. So I decided to do read-only. Again, like Ted said, read-only is simpler, but I wanted to do it the right way. Use the same data structures, the same types. So ints were 16-bit at that time. So type def things so that in the header, it looks like it is an ancient header. And do it in a way that when mounted, you're seeing everything as it was. You're seeing the same permissions, you're seeing the same timestamp, the same modes, the same inode numbers. It should look identical. Now, one thing I should mention is that modes, bits, they actually changed in between the 3rd edition and the 4th edition. They decided on, but after 3rd edition Unix, the mode bits that they use, this is read-only file, this is a directory, this is symlink, they have survived till today. They are identical from 4th edition Unix to today. So, but before that, you have the special cases. So, okay. So I decided to do this, and it was done. Didn't even take all that long because, MacFUSE makes it really easy. And, okay, so once I had this, I looked at the V7 format, and it was evolutionary. It was different, but it was not that different. So I thought, well, maybe we can have 2 examples and not 1. So I decided to do V7. And then they're both 16-bit. And 32V was a descendant of V7. It just used 32-bit things for, some of the on-disk stuff. So I thought, what, it's abstracted out well enough. It shouldn't be too bad to support 32E. So I decided to do 32E. Then I looked at the BSTs because I got 3 Unixes. And I looked at the BSTs and you know what? They were just a few steps ahead evolutionary. And it didn't seem all that much work to at least support one of the BSDs. So why not have a BSD file system as well? Okay. Now then I looked at this BSD did not have symbolic links. It did not have long file names. Now you got to have symbolic links. I mean, that's something that you expect. And we do have an example of a file system, which is BSD variable name, that supports all that. So why not have that as well? Now I have to draw a line somewhere. Even for me, I'm a reasonable guy. So then I thought, well, I had V6, but V6 really is V4, V5, and V6 because file systems are the same. So, and disk images and source code is available for ancient Unix from the like up till V7. And bits and pieces are available from older Unixes too. But the oldest surviving bootable disk images from V5. But they're bits and pieces from older Unixes. So for the sake of completeness, I decided to cover V1, V2, and V3, which is the V1FS, so that at least I can say that, I got all the ancient Unixes. So, okay. And well, there were tape images available. There were all kinds of tar and CPI images available. And, I like completeness. And you know where this is heading. So I'll just spare. So I just decided to do everything. So, so this is ancient FS. It is. It will be open source. It's a file system that it's modular. So I've implemented each format in a pair of files, a header and a C file. And even when the formats are very similar, I wanted to keep them separate so that even the commenting style, the header structures, and the names of the variables, I've tried to keep them as per the flavor of that generation, what they were thinking at that time, because, I can actually look at the old Unixes. So that when you read through it, you also get that evolutionary experience. And then they figured out that maybe they should have some defines for these things rather than using hard-coded numbers and, so on and so forth. And as far as possible, so what this means is, you can, so there's an article on this which I'll make available today, hopefully. So that explains where you can get these disk images, how you can mount them. So it's not just disk images, of course. It's tape images, it's archives, it's tar files, it's disk dumps. You can mount today's archives, obviously. You can use it on today's tar files. You can use it on today's CPIO archives. And so when I was doing this, of course, I was trying not to. So another thing is, like every good programmer, or hopefully, I don't really like working or programming. I mean, I think as the less you program, the better it is. So I wanted to make it easier for myself by abstracting things out as far as possible. So what I realized, and it should have been obvious, but you realize it better when you do something firsthand. It's the same pattern, and things haven't changed. If you go with this approach, you have inodes, and there's inode somewhere, there's a directory content somewhere. It's the same pattern. So essentially, all the on-disk file systems are the same, and the tape images, which are sequential in nature, they can be reduced to the same format by essentially making a hypothetical inode tree in memory. So I essentially ended up with an abstraction layer that I realized is actually helpful in writing this kind of file systems in general. And that would be the next API. So what I realized is that I've actually ended up with the fourth API for MacFUSE, which is if you want to do a Unix philosophy file system where you want to deal with inodes, on-disk inodes, and you essentially want to create or recreate a VFS in user space where you're actually asking, how you would ask for vnodes in the kernel. You would just ask for inodes, and it'll look up in a hash table and give you that inode. So you can miniaturize this and have an abstraction layer. That's actually generally very useful. So this gives us AncientF as an example, open source example, and also gives us an upcoming API, which you would be able to link to if you just find the source code in the tree, but it may very well be in the next version of, or some future version of MacFUSE. So that's that. So I was pleased with this, that we did cover all the file system formats from ancient Unix, and so this is this is a very old one of the first BSD logos. This was done by John Lasseter, I think. Now I want to, because I started this history thread, I do want to wrap it up by telling you. So what happened after that? Like the line I drew was I stopped at V10 and old BSD. So that would be, early 80s. What happened after that? So, well, at that time, the UCB people realized that the people who were working on FreeBSD, they realized that file systems are extremely slow, and they're not using the disk throughput. Like they're using like 4 or 5% of the disk's raw throughput, and this is because of how the file systems are laid out on disk. And folks like Kirk McCusick, who were doing research on how to write better file systems or how to lay them out on disk. So this is the beginning of the fast file system era. So you must have heard of, if you're into OSs, you must have heard of fast file system. Concepts like cylinder groups and how you lay them out on disk. So essentially, that would be UFS. What came to be known as UFS is what you could think of UFS as the Unix file system. But once they had the fast file system, then systems like, BSDs, Sun's operating systems, HP's operating systems, Next operating systems, NextStep and OpenStep, so they all adopted or used UFS. And even though I'm saying UFS, they were all different in that endianness would be different, block sizes would be different, even disk layout might differ in subtle ways. So it's not like, Leopard supports UFS, but you can't just take any of these old disk images or CDs and mount because it's not compatible. And this is something I personally have run into because when I was doing research for my book, I would often want to mount, next step CDs and disks or OpenStep CDs and disks. And the only way to do that would be to actually boot OpenStep or NextStep in a virtual machine. And this was in the PowerPC days. So it would be excruciatingly slow and time consuming. So often I would just not do it. I even remember doing a strings on a CD image because I knew what I was looking for. So AncientFS was done, and I looked at the history. And I was happy with the line I drew, which is that, you stop at this point and it's a good cutoff. And of course, UFS2 is current day BSD's file system. 4.4 BSD is what you would have in macOS 10. And of course, I like Sun and their operating system, so I have lots of Sun images I would like to mount. So I was toying with the idea. Now, this is pointless. It's a lot of work and all, but I was just thinking that, I have this really nice abstraction layer. And I got all these old file systems. And what about these? Because this covers like a whole generation of Unix from the beginning to now. But even I am not that crazy to actually go about writing these file systems. I mean, come on, right? But I couldn't stop thinking about it. So there's got to be a way. Of course there's a way. I mean, I can switch to Linux. Linux has the benefit of thousands of programmers working on the OS for way more than a decade. So I'm envious of Linux sometimes. Linux has a whole bunch of file systems that OS 10 doesn't have. And I booted Linux many times just for that purpose. And the Linux UFS implementation actually does cover all these. So then I thought, if I could take the Linux kernel implementation of UFS, the UFS family of file systems, and if I could get it to run on macOS 10 in user space as a MacFUSE file system, wouldn't that be nice? Now, that would be nice, but come on, that's silly. How do you do that? Well, why not give it a shot? So I decided to give it a shot. And I thought I would give it one night. Well, not necessarily to finish, of course. But I'll give it one night to do a reality check and see how I feel the next morning and if this is a go or a no-go. So, well, it was a long night. But it was a very fruitful night because I actually had it done the next day. So this says a lot about how the Linux code is written. Well, I wrote what you might call an ad hoc Linux VFS emulation layer, which is just a big file that does things on OS 10 that it doesn't have. But I also wanted this to be something long-term and real in that I didn't just want it to be a hodgepodge experiment that just works for one thing and doesn't work next time. So I tried to be systematic in what I was defining and redefining, and I wanted the UFS code base itself to be largely untouched because that's how I wanted it to be so that it can be portable. So that's how it worked out. That I have the UFS code in a Linux subdirectory largely untouched. And there's a linux.h and a linux.c. And it links against the whole thing. And it links against this abstraction layer that I created for AncientFS. I'm calling that layer UnixFS for writing Unix-like file systems. And it links into one big program called UFS, which supports all these formats. So you can mount all these file systems on macOS 10. And this would be open source too. So this was good. I mean, search for an example led to some really interesting and useful things. Well, this covers a lot of systems, but there are still some others remaining. System 5 family. I mean, that's a completely different, it's a different lineage. Now, Linux has System 5 family implemented too. And I just had this abstraction layer and this VFS emulation, as I call it, working. So to test how well this emulation layer was, I decided to spend one more night and see if I can get System 5 family to work. And it worked. So you got these file systems too on macOS 10. And at this point, I really was sick of file systems and inode numbers and all that. But I threw in Minix as well. So we talked of 3 APIs, and this is the 4th upcoming API. And this is what we have. So today's MacFUSE 2.0 release, in the source tree, we'll have 4 new families of file systems checked in. Open source. The Linux stuff is obviously under GPL. And you can use it to mount any of these types that are listed here. So hopefully this will be useful and interesting on macOS 10. And I can tell you from experience, if you want to import other formats from Linux, ext2, whatever you might want to, it is possible. It's reasonably easy. Let's see where this evolves. You know, if you have like if you are a virtual machine distributor, you want to support Solaris and BSD, their current operating systems, and you want to give the user the ability to mount those disk images, you know, you might want to use this. So that's about it. And taking a page from the playbook of you-know-who, there is one more thing. And now for that, I would actually have to go to the demo page. And I promise this would be the end of it. Everything has to have some reasonable lines drawn. So I'm going to mount. So Ancient FS tells you what all it supports. So I'm going to mount. Now one thing is that old Unix file formats didn't always have magic numbers. So you don't know what it is. So you have to tell Ancient FS what it is. If you don't, it'll try hard to do some sanity checks. You know, the number of inodes, free block list, and all looks sane. But you know what? It may just be fine, even though it's garbage. So you may have an empty mount. So if things have magic numbers like tar and R, it'll recognize it. Otherwise, you need to tell it what it is. So I'm going to mount V5 and V6. So you do a mount, it'll tell you what's mounted where. You go to V5, you see the ancient Unix tree there. Now you can do a find, you can go look in dev, you'll see the correct block device, whatever. I mean, like I said, everything would be correct as far as possible. Now, if I go in here, user sys, I believe. So this is ancient Unix kernel source code from 5th edition Unix. Now this is not really related to file systems, but wouldn't it be cool? So, for example, if I go in bin, I see things. I actually see, do I see, oh, this is user bin. Let me go in bin, and I see CC. It's a C compiler. File CC. It's a PDP-11 executable. Now, wouldn't it be cool if we could compile the 5th edition Unix kernel using this disk image I just mounted on Mac OS X? How would you do that? Well, the compiler's right there. Let's see if we can. So I'm going to, now these are read-only file systems, so I'm going to go to another directory where I copied the source tree. Okay? And I have the script here, make unix.shell. So what it does is it sets the like ancient FS root to something, and then it just calls binaries in that particular directory CC and just tries to compile these things. Mind you, they're PDP-11 binaries. So let me see. I don't know if the ancient FS root is set. Let's give it a shot. It's pretty fast too. And does anybody remember this number, the size of the kernel? This is the binary I was talking about. So what we have done is we have executed PDP-11 binaries on OS X. There's no smoke and mirrors here. I can actually do volumes v5 bin ls, and it'll work. Now, this is for really hardcore Unix people. The answer is on the net. But there's one last thing I want to show you. And if you don't know, you should go look it up. But the move command in the 6th edition Unix had this error message. Let me remember if I can reproduce it. If you do something like this. So look this up on the net. So like I said, so this is unrelated to file systems, but so this has a problem to begin with, which is unlike Linux and BSD and some other operating systems, OS X does not support, like even if you emulate things, OS X does not support extending the binary format, like handling capabilities of the kernel. You cannot have bin format L for things like that. So this is another side project that tries to solve that. And I'll talk about this some other time. You'll see like open source releases and whatnot. So I just wanted to give you a preview of what, but it seemed to fit in very well with the Unix and all here. And now I'm truly done. Thank you. Any questions? Then we can quickly do a Q&A. Otherwise, it's been a long talk.
Could you just quickly say how you get the PDP-11 bits to execute on Intel?
I used a, this is not my work, I used an existing, it's a standard approach that you will use, that you will translate you will emulate the instructions, and you will handle the system calls natively by doing open, close, read, write, like how you would on the native system. Okay? Thank you.